either applied physics or fundamental aspects of different phenomena in nature, like he can use turbulence, problems involving earth science, and also Professor Swing has been winning many awards worldwide in different aspects of the science, in geophysics, in physics, and applied mathematics, and also in the physics community. He is a Boltzmann medal winner. So it's great pleasure for me to invite Professor Sweeney to telling us something about his work. Professor.
Well, it's a great pleasure for me to be here in Brazil again, in particular, to be at this meeting. I want to talk about some of the work of the past 50 years since the Brazilian Physical Society was organized, and some of the problems for the future. In the 1960s, at the time the Brazilian Physical Society was organized, in the statistical physics and condensed matter community, there was interest in understanding this result from a set of experiments that were organized by Guggenheim. This plot was actually made in 1945, but it was a subject at conferences of a lot of discussion to understand this curve and the exponent that describes it. There were experiments on multiple fluids, and they all fit the same curve. For the density difference between the liquid and gas phases is a function of the distance, the temperature difference between the critical point and temperature of the measurement. Now, it was noted that magnets behave in a similar fashion. This set of data goes way back. Curry discovered that magnetization of magnetite, the most common magnetic mineral, goes to zero at a temperature of whatever, 573 degrees Celsius. And it's a reversible transition. If you lower the temperature, the magnetization follows the same curve. And you look at the two curves for magnets and for fluids, and they look rather similar. And in fact, they both are described by the exponent characteristic, exponent 1/3, within the uncertainty of the data. Well, this was a dilemma in the 1960s. They had the Landau theory of phase transitions, which basically assumes free energy is analytic at the critical point, so you expand it in the Taylor series, and you get the exponent beta equals 1/2. Well, 1/3 is significantly different from 1/2. And that was a puzzle. It was also surprising that all fluids and ferromagnets seem to obey the same exponential law. Now, computers were becoming available, and very industrious graduate students to solve the Ising model for more and more terms. And it was interesting. You get a value for the exponent for the coexistence of two phases very close to 1/3, which was the observed value. The calculations were made more and more accurate, but they never approached the value 1/2. So this was a puzzle. In the 1960s, I attended many meetings on phase transitions. Go to APS meetings, and there are many sessions about phase transitions, trying to understand this behavior. In 1966, when the society was formed here, I wrote a paper about how the fluctuations near the critical point, spontaneous fluctuations, decay very slowly, critical slowing down, as it's called. Well, this was all, the understanding of phase transitions was all pulled together by very nice work by Ken Wilson using the normalization group theory, which he had learned as a particle theorist, and applying it, and he got a Nobel Prize because his theory applied very generally. If you know the dimension of the system, whether it's two-dimensional or three-dimensional, and if you know the dimension of the order parameter, then you can predict what the set of exponents characterizing the transition should be. Now, something entirely different happened in the 60s. Ed Lorenz was a meteorologist at MIT, and he was interested in understanding how far in the future can you predict the weather, or can you even predict climate? Well, the atmospheric and oceanic systems have enormous numbers of degrees of freedom. Let's simplify the problem, and he really simplified it, because he got down to 3 coupled ordinary differential equations, no spatial dependence here, and studied their behavior on his computer, on the computer at MIT, and he found that the solutions for a particular set of parameter values here, the the sigma and the r and the b, 3 parameters, for a particular set of parameter values, the solution wasn't time periodic or even quasi-periodic, but it was non-periodic. And if you draw it in a 3-dimensional space spanned by the UVW, you get this object shown here. And if you take 2 points close together, so that each of those represents the system at an instant of time, and you look at the evolution in time, so you follow the trajectories, and they separate exponentially fast. So he said, there's a problem if you're a weather forecaster and predicting the weather long in the future, because small errors grow exponentially fast. This paper wasn't recognized in the physics community until the 1970s, and then everyone began reading it and talking about it at conferences. And in 1972, he gave a talk at the American Association for the Advancement of Science meeting, and he entitled it, "Does the Flap of a Butterfly's Wing in Brazil, okay, cause the tornadoes we have in Texas?" Right? Interesting choice of locations to illustrate his point, right? So this was a puzzle. Now in the 70s, there were a couple of mathematicians, David Ruel and Florence Hawkins, who wrote a very mathematical paper which was unreadable by experimental physicists and engineers who were interested in the subject because of the title of the paper, On the Nature of Turbulence. Use fiber bundles and all, anyway. But what caught the attention of people was the same kind of behavior that Ed Lorenz had described, where you have exponential growth of uncertainties, and they termed this object here a strange attractor. Not long after that, Lee, a student of Jim York, and Jim York published a paper in 1975, Period 3 Implies Chaos. That's the first use of the term chaos in the sense we use it now, that is exponential growth of uncertainties or errors, a positively Lyapunov exponent, if you like. And that fairly rapidly became a standard word in the English language, and I think many other languages. Chaos is a term that students know when they come from high school. It's a term. You can even say it at a cocktail party to a lawyer, and they have some faint idea what you're talking about. Now, a few years after that, Mitchell Feigenbaum was studying a one-dimensional map with a unit interval into itself. So you could have various forms of a one-dimensional map. He was studying them in general, as long as they had a parabolic maximum. And this is a logistic map here, and this is the value of xn after transients have decayed. No matter what your value is initially, you asymptotically approach this value, which is plotted here, as a function of the parameter r. And r goes here from 0. It says 1, it should say 4. I see that error. Okay. And beyond a certain value of r, 3 here, instead of the map returning to the same point in every iteration, it alternated between 2 points. So you have the period, it was not one cycle, but 2 cycles. So you have period doubling, and then you have, at another well-defined value of r, another period doubling, so the period is 4 cycles before you return to the original value of x. And then 8, 16, and so forth. You have an infinite sequence of these, but the interval for each period is smaller than the previous one by a factor which Feigenbaum calculated. So you have quickly an accumulation point of the sequence. The sequence terminates here at period 2 to the infinity at r equals 3.61. And beyond that, you have chaotic behavior. But in this region of chaos, as you go from r equals 3.6 to 4, there are intervals that are periodic. Periodic here, you can see period 3 is very evident. See some range in r where you have 1, 2, 3 values of x for any value of r. What?
I think you want n minus 1. X n minus 1.
Okay. I made the slide yesterday. I mean, I meant to prove everything, but okay. Well, it wasn't long after that this period doubling sequence was actually seen in an experiment. The paper of Feigenbaum was rejected by Physical Review Letters. They said, this is mathematics. Has nothing to do with physics. But here's an experiment which exhibited the period doubling sequence by Albert Liebscher and his student. In convection, a fluid contained between 2 plates, and they increase the temperature difference between the 2 plates, and they go from periodic oscillations here, there with period t, and then you can see alternate peaks have a little different amplitude, so that's period twice as long, and then here the period is 4 times as long, and so forth. You can't see many of these doublings because the interval over which they exist becomes so small, so fast, but you can get up to period 8, and if you have a very precise experiment, maybe period 16. That was 1980. A year later, there was some work done down in Texas and on a chemical system, a chemical reaction called the Belousov-Zhabotinsky reaction. It's just a chemical reaction which involves several feed chemicals, and you can vary the concentrations of those chemicals or vary the flow rate in the reactor. And you go from a state which is invariant in time with all the concentrations constant. This is a well-stirred reactor, so this is homogeneous, no spatial patterns. But you reach a certain value of the concentrations and you get periodic oscillations. And they exist over a wide range of chemical concentrations. But you continue varying the chemical concentrations or the flow rate, and you get to a point where these oscillations that you have, so this is concentration of the bromide ion, which is produced by the reaction, easily measured with a bromide ion probe sticking in the reactor. And beyond a certain point, this period doubles, and you see alternate peaks here. Alternate cycles have different amplitudes. But it's periodic, just twice as long a period, and then you can see period 4. Now, beyond a few period doublings in the experiment, we recorded time series of the concentration of the bromide ion as a function of time. Ooh, this is pretty long time. These are slow oscillations. Typical period of oscillation is 2 minutes. That's not very convenient. The data information rate is so slow. You have to wait a long time. But then the question was, is this really the kind of chaos that had been discussed in the 70s, or was this just a noisy system? Was this random noise, or does it have some deterministic character? So we made a movie off of an oscilloscope. We got a used camera for free, 16 millimeter black and white film, and made a movie, which I'll show now. And we plot here on the horizontal axis the bromide ion concentration at an instant of time, and on the vertical axis is the bromide ion concentration at some later time, t plus tau. Tau is arbitrarily chosen at that time. And then we watch the orbits. The system is oscillating, so it's going to go around, and and the question is, what is the value of the concentration when we cross this line? And we let that be xn, and then we have a sequence of numbers xn, x sub n plus 1, x sub n plus 2. And do they have any relationship to one another if we plot them in a graph of xn plus 1 versus xn? So that's what you see here. Is it possible to turn off these lights? Excuse me? Is it possible to turn these lights on? Okay. Okay. So here we go. This, yeah, that's better. Thank you. Yeah, you can see. You can see the jitter in the movie frame too. But it goes around, so that's xn3, x3. The next one is x4. x4 plus versus x3 is plotted there. So we see if we get a scatter plot of points, or do we get some set of points that have a relationship with respect to one another. This is sped up. Every point takes 2 minutes in the lab. Okay. And you see, you get indication that the system is deterministic. Given xn, this map here, this curve, gives you the next value. The system is not periodic, but it is nevertheless deterministic. And we have something that might be a strange attractor that was discussed by Ruel and Tockett. So beyond the accumulation point for that sequence of period doublings, where you get the chaos, and you look in the chaotic region, I said there are periodic windows. Here is one periodic window. This is a time series showing period 6 oscillations, and then it repeats. If you look on the map, then you can see the iterations of the map. And we talked to various people about this, and a mathematician referred us to some work by Nick Metropoulos, who the theorists in the room know, who did a lot of work mathematics and on computers, analyses. At the peak of the map, you iterate to the right, and then the next time you iterate, you move, you go right side of the peak. And here you see you go to the right, and then back here, you're on the left side. So we go right, left, and then from this point, you iterate, and next time you hit the map, you're to the right of the peak. So that's an R, and you go 2 more iterations to get back to the beginning, and they're both on the right side of the peak. So that's a symbolic sequence of Metropolis, Stein, and Stein, RL, cubed. And we found a lot of these periodic states embedded in the chaos, and they were all in the order predicted by Metropolis and Stein, MSS. Now, this is another strange attractor obtained from a chemical experiment, and we analyzed it in different ways, and we spent years analyzing these data and wrote several papers about computing the fractal, the non-integer dimension here, and the rate of separation of nearby points, the largest of the Lyapunov exponents. Did a little work on the next one as well, but the largest Lyapunov exponent. And then I said we reconstruct an attractor from a time series by taking the measured variable and giving a time delay. Well, how do you choose that time delay? We talked to mathematicians, and they say, well, any time delay works. Of course, if you make the time delay very small, all points are the same. And for some time delays, the attractor looked much nicer than others, and we worried about that for several years. But then we found a way to use information theory to compute the optimal time delay, and that the mutual information turns out to be very useful. In fact, these couple of papers have thousands of citations, so somebody's found it useful. Now, I've been talking about homogeneous systems. What about the spatial dependence now of systems that are driven away from thermodynamic equilibrium? In Turing's last paper, he wrote about how patterns form in biology. Of course, he was a mathematician, and so he solved a mathematical model, and it was a pretty simple model with only 2 mechanisms in the equations. One was chemical reaction, A plus B goes to C, no back reaction, just A plus B goes to C, and the species A and B have different diffusion coefficients. So it's a reaction diffusion system. So the concentrations could vary in space. And he found, for certain parameters in the model, certain values of parameters, that a pattern, spatial pattern, would spontaneously form. And he wrote, a system of chemical substances reacting together and diffusing through a tissue. He's really interested in how patterns form in biological systems. Although it may be originally quite homogeneous, may later develop a pattern due to an instability of the homogeneous equilibrium. That was his last paper in 1952. So we worked for a number of years looking for Turing patterns, and others did as well. And it was found back in the 60s by Zhabotinsky in studying that chemical reaction, the Belousov-Zhabotinsky reaction, that you could pour chemicals together into a petri dish with a piece of filter paper in it, and spiral patterns would form, and the chemicals would be consumed as you evolved from the non-equilibrium state to equilibrium. But we wanted to have a system where we could maintain a non-equilibrium state under control and vary the distance away from thermodynamic equilibrium by, like a fluid system where you fix a temperature across the plate, you can vary that temperature difference from the top to the bottom plate. So we designed this reactor. This is not the first design. This was many, many designs. It didn't work, which I won't talk about. But this is a reactor which is fed with an oxidizing chemical and well stirred. So this is a reservoir of oxidizing chemicals, and this is a reservoir of reducing chemicals. There's no reaction in the reservoirs. But between the reservoirs is a thin gel layer. So you have a concentration gradient across the gel, and the chemical reaction occurs, oxidation reduction reaction occurs there. And you vary the concentrations of the two reservoirs, and for most concentrations, you get no spatial pattern. But you can look to see if you have a spatial pattern by looking down from the top with a camera through this system, looking through the gel, and the chemicals absorb light differently, so you get a pattern if one should form. And it was found at a certain concentration, critical concentration of the oxidizer and reducer, you had a bifurcation, continuous bifurcation, reversible bifurcation, no hysteresis, the onset of a pattern, a pitchfork bifurcation, that is, the amplitude of the dots grows as the square root of the distance away from the transition. And in looking at this pattern, if it's really a Turing pattern, then the spacing between the dots should be related to the reaction rate constant and to the diffusion coefficient of the chemical species. So those for this reaction were independently measured, the rate constant and the diffusion coefficient. And we computed the wavelength and compared it to the measurement, and it agrees right on with Turing's prediction, Turing's simple model. So the instability you see leading to a spatial pattern was studied by Turing and various fluid dynamicists in the 20th century using a linear stability analysis. So you take your base state near equilibrium, you can solve, particularly if the system has nice symmetry, you can solve and get the state that's on the thermodynamic branch, like the thermodynamic equilibrium, but just a small gradient away from it. And then consider what happens to an infinitesimal fluctuation, a little perturbation. Does it grow or does it decay? So then you have the equations that you can linearize in that infinitesimal perturbation and see if the growth rate of that disturbance is positive or negative. And here it's negative for all values of the wave number, but if you vary the control parameters, say the concentration gradient, the chemical experiment, at some point the growth rate goes to 0 at a particular wave number, particular length scale, and beyond that the perturbation grows and you no longer can use linear analysis. You have to use the full nonlinear equations, but you grow into a pattern. And that's the kind of analysis that Turing did, and it's the kind that many others did. That growth rate doesn't have to be real, it could be complex, in which case you get traveling waves. Here are spiral waves. This is the white here is the front of the wave, and you have oxidation reduction wavefront that collides and annihilates, and the waves propagate on and on. So this is sustainable, and that kind of spiral pattern is seen in, oops. Whoa. Oh, there we go. Okay. So in the human heart, you have a pacemaker here, sinus node. It sends a signal for the heart to pump, the heart chambers to pump, and that works all and well most of the time. But if the pathway is broken or damaged in some way, the pathway breaks and spirals form. Spiral waves in the heart form. Here's one picture in a dog heart. This isn't healthy. It leads to tachycardia because the spirals rotate faster than the pacemaking from the sinus node. And you have very rapid heartbeat, and that goes into irregular heartbeat, fibrillation, and you die. That's not good. And more than 100,000 people in the U.S. a year die from this fibrillation rising from the spiral wave. So there's a large number of medical centers now that are studying spiral waves in this excitable medium to understand how to stop the spirals, interrupt the spirals, change the phase with a small voltage, not 25 kilovolts, but with very millivolts in the right way, the right point of the cycle, and return to normal rhythms. Okay, I want to talk about an older problem, even a fluid contained between two concentric cylinders was studied by G.I. Taylor in the 1920s, and he rotated both cylinders. One was some angular velocity omega inner cylinder, and this one outer cylinder, and there's some gap. The fluid is in this gap between them. So for small rotation rates of the two cylinders, or differential rotation rates, you get a flow that varies, that's azimuthal at small rotation rates, because the solution to the equations must have the symmetry of the boundary conditions, Navier-Stokes equations, for a system close enough to equilibrium. So the parcel of fluid just moves in a circular path, and as you increase the rotation rate of the cylinders, or the differential rotation rate, at some point an infinitesimal perturbation will grow and you develop a new pattern. So Taylor carried out a linear stability analysis and found that a pattern forms that consists of vortices that wrap around the inner cylinder. And as shown in the picture up here on the left, he did the experiment first. He's a good experimentalist, does it? And then he said, well, let's see if I can understand what this means. And he spent several years working out the theory in a beautiful way. We have in his graph, this is from his paper in 1923, the rotation rate of the inner cylinders on the vertical axis here, and rotation rate of the outer cylinders on the horizontal axis. And right here, both cylinders are at rest. So in this quadrant, they are rotating in the same direction, and in this quadrant, they're rotating in opposite directions. So he started at this point and moved up away from the equilibrium state. So this was the equilibrium state, and he found the transition in experiments given by these red dots here to the onset of these Taylor vortices, what are now called Taylor vortices. And in his analysis, linear stability analysis, he got these points which are green here. Fantastic agreement. He should have gotten a Nobel Prize. He really should have. Because he had found the onset of instability in a fluid in an experiment and mapped it out very nicely. He looked at cylinders with different radius ratios and all kinds of variations before he published. And before him, Lord Kelvin, Lord Rayleigh, various other names well known to people in this room, had attempted to compute the point at which a fluid would become unstable as you imposed a gradient in temperature, pressure, rotation rate, something, moved away from the equilibrium state. And they all failed. partly because they chose very difficult geometries, but they began to think maybe the Navier-Stokes equations for a fluid aren't correct, or maybe the boundary conditions that we've been assuming, the no slip at the boundaries, aren't correct, or maybe both are wrong. So there was, in the teens, after Lord Rayleigh analyzed convection and didn't get the right answer, or the answer he expected, there was great consternation over the validity of the fluid dynamic equations or the boundary conditions. But this demonstrates their validity, and as Taylor, this is a quote from Taylor's paper, said, "Look guys, you failed." Well, you might ask, what happens, what happens above this line? If you keep going up, above this line, if you rotate the cylinders faster, does the flow just become turbulent, or do you maintain the time-independent vortices for high rotation rates? Taylor's only experiments showed that you get, if you go up in the rotation rate of the inner cylinder, at some point you get, on these axisymmetric time-independent vortices, you get traveling waves. Beyond that, it was open question what you get above this. David Anderick in our laboratory decided to look to see what might happen if you go above the curve, and this was 30 years ago, 1986, and he observed these instabilities by going up this way. So you see there are about a dozen different states. Each transition corresponds to a change in symmetry of the flow, spatial change, or space and time symmetry changes. We were interested in particular in looking at what happens as you go to high rotation rates, where the flow becomes turbulent. How does the flow become turbulent? Well, Landau, 1944, says a fluid in general becomes turbulent by going through a sequence of bifurcations. And here you see a sequence of bifurcations as you go away from equilibrium. And each of the bifurcations will bring an additional characteristic frequency into the dynamics. And each successive frequency would be incommensurate with the previous frequencies. So after you've had a number of such transitions, you don't need too many to have a pretty complicated flow if you have 4 or 5 or 6 or 10 frequencies which are incommensurate. So an experiment was undertaken by Jerry Golub and myself to test Landau's idea. And we go up in, now with the outer cylinder at rest, take a simple case, and you see here Taylor vortices. You go up in rotation rate of the inner cylinder. At a well-defined rotation rate, waves form on these vortices, so you have a periodic system. And then you go up faster, and you have a system that begins to become turbulent. So look carefully in this region here to see how do you go from wavy vortices to the turbulent, weakly turbulent flow. We recorded velocity as a function of time in the fluid. From that, made a time series where he transformed that to get a power spectrum to determine the characteristic frequencies of the flow. And here you see something very simple. A power spectrum has one characteristic frequency. This is frequency on this axis, which I failed to label. Frequency in units of the cylinder frequency. So you have one, that's the frequency of waves passing a point of observation. Now you go higher in Reynolds number, and there's another well-defined transition, rotation rate of the inner cylinder, where a second frequency comes in. And here you can see the second frequency, and you have sums and differences, but all of the components here are related to some integer times the first frequency, plus or minus another integer times the second frequency. So there are really only two fundamental frequencies. Then we went to higher Reynolds numbers, and we never found a well-defined sharp frequency, characteristic frequency. But the noise here began to rise and continuously rose with increase in Reynolds number. And we had the good fortune, when we found that, to have a visit by David Ruel, who I'd never heard of. And he said, "Oh, you found the strange attractor," which meant nothing. But also talked to others, Joel Lebowitz and Jim York, and decided maybe that's chaos. So we analyzed that through a period of years. And when you have the flow with two frequencies in phase space, you have the orbits lie on the surface of a torus. And you can see that. You cut through the torus here. It constructed in 3 dimensions. And you see the points lie on the surface of a torus in that doubly periodic state, 2 characteristic frequencies. Now we can increase the Reynolds number a little bit, and the torus begins to wrinkle. See the wrinkles here, and you can see them here. Signal to noise is not too good, but it begins to wrinkle, and it's a wrinkling of the torus that Ruel and Tockins were talking about. So this is a chaotic state, and not going to chaos through period doubling, but through the wrinkling of a torus. Now what happens if you go very high Reynolds numbers, 100 times the Reynolds number here? You still have Taylor vortices, but they have a wide range of spatial scales, and it's very complicated. And how do you analyze that? Well, these low-dimensional attractors that we constructed for the problem we were looking at, we would construct a phase space up to 4 or 5 or 6 dimensional, is not sufficient and is not very productive in understanding turbulence. But recent work by a number of people, I just mentioned one thing. So this is a very active area of research. What can you learn about turbulence by looking in phase space? In a strange attractor, in the phase space of high dimension, where the trajectories separate exponentially fast but are very complicated and irregular, you have a dense set of periodic orbits. And if you can locate those low-order periodic orbits, you can make much better forecasts of future behavior than by other means. And that's what's been done in this very nice paper here by Michael Schatz and co-workers, and some work by Predrag, Svetanovich, and various others are looking. So this is just a topic which is developing. It's not something that is extensively used or really understood. How do you get that? I don't know how I'm doing on time. Okay, so I'm going to talk a little about growth processes. So suppose we have an oil layer between 2 plates, and a thin oil layer, very closely spaced plates, and we push air into the oil layer, and looking down at the top, that little bubble of air grows into these fingers, which split repeatedly and form this complicated structure. And I just saw a very nice paper on this by 2 guys who are now in, 10 minutes, okay, here in Natal on a model that gives, this is of course it's a continuum process, but a discrete model called diffusion limited aggregation gives pictures that look the same. And understanding this relationship between this discrete model and a continuum equation has been a long-standing puzzle, and it's addressed in this paper. Okay, so everybody knows about fractal dimension. You can take a plastic bag, like off a CD wrapper or a trash bag that line the trash cans. If you get one, you tear it, you know the edge of it is wrinkled, right? Whether it's 25 microns thick or 30 or 10, doesn't make any difference. It's wrinkled on the edge. You look at the edge here, and you see the wrinkling. Now, this is, so you have two fingers. There's a finger and finger, just looking at the edge. So you have more area where on the edge where the plastic is stretched, and it can no longer lie in a plane, has to leave the plane, and it forms these waves, and here you see waves within waves within waves. Because here's a stretch of this is taking a single photograph and enlarging it, going down, zooming down in scale, photograph looking on the edge, and here this is 30 millimeters across here, and then you take this section, multiply by 3.3, magnify, and you get this, and you magnify this piece of the 3.3, and you get that, and so forth. You go down through the successive generation. So you have a structure which is self-similar. And not enough time to explain the physics, but you can do some analysis. But that problem is not understood. You can do simulations and get the same result as in the experiments. You can look at graphene sheets or other thin sheets that wrinkle, have fractal structure, but understanding this is the amount of stretch versus the distance from the edge of the sheet. What is the necessary and sufficient condition on the function and its derivatives to give you a fractal structure? Because you don't necessarily get one. If the stretching is not too large, you can just get waves. And you can confirm this by going to the grocery store and looking in the leafy vegetable part of the produce. You'll see kale, which has fractal leaves, and you see other kinds of lettuce that have a single leaf, a wavy leaf, and some lettuce leaves don't wave at all. Others have waves with two frequencies. What are the conditions? It's in nature, advantageous to have more surface area. The endoplasmic reticulum is all wrinkled, so it has more interaction with the various biochemicals, so forth. And you can look at, that's plastic sheet here. This is the leaf of a beet. See, it's similar. Here's the violet. Here's a particular kind of lettuce. And so, is there some kind of universality? Who knows? It's interesting that each of these examples has a fractal dimension of about 1.71 for reasons unknown. And I said fractal wrinkled graphene, which is being considered as a potentially very effective electrode for batteries because it has fractal character, a lot of surface area. So, okay. Now, what about the convection problem? Let me just go quickly. This is just a very simple problem, which I'll close now in a little bit. Not yet. By saying I think this is a fundamental physics problem that relates to the future of our Earth. It's a really simple problem, and it's unsolved. What could be simpler than having a parallelepiped box heated from below and fixed temperature at the bottom, at the top, and you ask the question, how much heat flux is conducted as a function of the temperature difference? Now, you know the equations. I'll skip that. You get, at onset of convection, you get the convection rolls. And now let's look at the problem if the height is large and delta T is large. Okay, so the height of the tropopause, say 10, 12 kilometers, and the temperature difference between the warm Earth and the tropopause is maybe 60 to 70 degrees Celsius. And how much heat is conducted? The vertical time average, spatially average heat. Answer is not known. And the scaling is not known. Not even for this simple problem. If you ask, this is the vertical heat flux, this is some number, beta. What is that number? Well, I'm mentioning, if you want to forecast the weather, or more importantly, predict the climate, you ought to be able to solve a simple problem like this. How can you make a 100-year prediction of climate if you can't solve a simple physics problem like that? You can talk about the Earth's mantle too. You can talk about the circulation of the ocean, also driven by convection, and it's not well understood at all. The red curves here are the ocean currents. We know the Gulf Stream very well here. They're warm currents. The cold currents, where the warm currents have gone north, like to the North Sea here, and then you have downwelling and they flow along the bottom. So the blue curves are the cold currents along the bottom of the ocean, and that's an artist's rendition for the paths. The red currents you can measure location with satellites, and this is like a snapshot in time because they move around. Okay, now does that make a difference, having these currents here? Well, you take the Gulf Stream here, it goes north, takes these tropical waters, warm waters carries them up, and they keep Europe warm. How warm? If you look at the global average temperature at a particular latitude, averaged over the whole latitude, and look at the deviation locally, you can see here in Northern Europe, it's 10 degrees Celsius hotter than the average at that latitude over some region, and 5 degrees hotter. So, and the Gulf Stream is losing, its current is decreasing. No one understands why. Generally, Antarctic circumpolar current is decreasing. Unknown why, all right? It'd be nice to understand these things. So what about convection relevant to the climate or to weather? Well, the dimensionless number, the Rayleigh number, is greater than 10 to the 20th, whereas what is the situation in physics? Well, it's sad by comparison. The best numerical simulation goes to 10 to the 10th. Possibility of going 10 to the 20th in a numerical simulation is far beyond my lifetime and the lifetime of the youngest person here. It's just not going to happen. 12 orders of magnitude. Laboratory results are difficult. There are a number of groups doing experiments. They're not in agreement. And let me see, there are analyses of models with various assumptions that give different values ranging from 0.28 to 0.5. But some very nice work is underway by Charlie During, looking at the Navier-Stokes equation and deriving rigorous bounds on the value of beta. But I won't go into those. This is a simulation done at Max Planck Institute in Göttingen at a Rayleigh number of 10 to the 10th. So the troposphere is like 10 to the 22, 12 orders of magnitude larger, but you can see it's pretty complicated at Rayleigh number of 10 to the 10th. Okay. Okay. Okay, this shows you that the best experiments that have been done to date on convection, running up to Rayleigh number 10 to the 14th, disagree. It's a big, amongst these groups, it's a big controversy. But, and this is fundamental limits set by analysis of the Navier-Stokes equation. And I'll conclude. All right, so we see patterns spontaneously emerge. They often form fractal patterns, and there are a number of examples. There is no general theory, good statistical theory for equilibrium systems, for systems away from equilibrium. You can extend the equilibrium statistical mechanics up to the first bifurcation. Beyond that, there's no general theory. And things that we all accept, like fluctuations in number of molecules in a box in this room, go as the square root of the number, the RMS fluctuation. They don't behave that way if you're far from equilibrium. And what can one do? You can maybe work with the equations of motion, try to derive rigorous results. You can work with statistical mechanics, or you can do experiments or models, all of which contribute to the understanding. So, am I completely out of time? I'll stop. Huh? Okay.
Thanks so much for this very nice talk. So we have time for a couple of questions.
Okay.
No? Okay. Do these unstable periodic orbits in turbulence have to do with the so-called coherent structures in turbulence?
Not directly. That's I had slides on Lagrangian coherent structures. So this is another direction in which progress is being made, and we're using it in our group to study transport in the oceans and trapping of material in vortices, identifying the invariant curves through the Lagrangian coherent structures that are material lines. No material crosses those. So there's George Haller is one of the leaders. Jared Marsden he's no longer with us, but George Haller has a series of papers starting in 2001, and he's just turning them out. But many groups are trying to exploit those ideas to gain some understanding, particularly of transport.
Can you say anything about the business of stopping fibrillation by putting a small vIvo set of particular?
No, if you construct if you can take a short time series of the fibrillating heart and construct an attractor and see at some point it is susceptible, the basin of traction is shallow. Maybe a small voltage can get you into another state, into the periodic state. And there's work being done at McGill University, at Harvard University, Duke University, by medical doctors together with mathematicians and physicists.
Okay, since we're up with time, let's thank the speaker. Thank you very much.
Thank you so much.
Obrigado. confirm. Sign Solberg.
Schöberg, yeah.
I would like to introduce Professor Sven Solberg. Professor Solberg is a professor emeritus in science education, working at the Department of Teacher Education and School Research in University of Oslo. He is honorary professor at the Department of Science Education in Copenhagen University, Hong Kong Institute of Education, among many other universities. He was educated as a nuclear physicist, have a master in education, and a PhD from Oslo University. Professor Solberg was awarded with a lot of prizes and awards from universities and governmental entities. He was involved with many educational problems in Europe and around the world, developing policy initiatives in the field of education in programs such Eurodice and Horizon 2020, one of the biggest European research and innovation programs. He was responsible for comparative projects on pupils' interests, attitudes, perceptions, importance to science teaching and learning, such as the ROSE project. He was a member of the OECD working group on the declining interest in studies in science and technology. He was a member of numerous international scientific committees involved with different kinds of education assessment initiatives, such as international assessment for the evaluation of educational achievements, European cooperative projects on science and mathematics education, female education in mathematics and science in Africa. He has been involved in many curriculum reforms, wrote textbooks for all educational levels. His current research interests is on social, cultural, and ethical aspects of science education development, gender and science education in developing countries, and also international comparative research. But in the latest works, he dedicated to build a critical approach to questions related to scientific literacy, public understanding of science, and the use of implications of large-scale comparative studies in science achievements, like Pisa and TIMIS programs. So it's a pleasure to have him talking about international education assessments, a central problem to education, but particularly an extremely important question for the science education, since we are living a huge educational crisis in Brazil. I would like to call your attention that Professor Solberg proposed a discussion session about his presentation today with people interested on international assessment. This meeting will occur tomorrow, 2 p.m. as Symposia 2 at Cedro 1 room. So, Professor Solsberg, thank you very much to be accepted our invitation. Please, the floor is yours.
Thank you. Thank you so much for the introduction. I come from Norway, so I'm happy to live in this area that we just got described as getting 10-15 degrees more than we actually should have had if it for the physics of the oceans. My talk will be more of a, should I say, a pre-dinner talk compared with the last one. So, and there will be a discussion session tomorrow to follow up with protests, with discussions and implications and so on, to go a little more in depth. But you see here from my title about Pisa testing, that I will come back to, is a kind of a global arms race. And I think it is, and this is my conclusion and argument, that this is to the detriment of the students' engagement in science, the motivation, the curiosity, and I would also say for the future recruitment to science. So that's why I think it should be a concern for everybody working in science and here in physics in particular. Now, when I was a student of physics and later of educational psychology, I had two heroes, and the one was obvious, that was Albert Einstein, and the other is also quite obvious, it's Paulo Freire. So it's a pleasure to be here in Brazil and to say this. These are just some of his books that have had wide range influence on educational thinking and debate and policy worldwide, I would say. Pedagogy of the Oppressed is a famous book. A Pedagogy for Liberation is a famous book. The Politics of Education and the Pedagogy of the Heart. So, and these are the books, and they are translated and are in many, many languages and still have an influence. So I think you should be proud here in Brazil of the heritage from Paulo Freire. Now, I would also say that science and democracy build on common ideals, common values, common ideals. The openness for argumentation, respect for evidence and rational discourse, that we should listen to others, we should have critique, we should have discussion and an open mind. Now, but as we all know, that this, although these are good ideals, they are not always the case in reality, neither in the science community nor in so-called democracies. And I think we have good examples of all this. But they are still values and ideals that we strive for in science and in democracy. So that's a kind of starting point. And also I think it is talking to an audience like this, which consists of professional physicists and professional scientists. We should be aware when we talk about school and we talk about education, we should distinguish between science and mathematics as academic disciplines, which I think a conference like this is a manifestation of the universality of that. You can come from different corners of the world, and the science and mathematics, and the physics and the mathematics are really the same. They are shared, they are universal. But school science, and indeed not only school science, but the school curriculum, it needs, and now in particular when we talk about basic education, compulsory education for everybody, it needs to be put in the context that is deemed to be relevant in the life of the learners, for the future of the learners, and it cannot be universal and common because people live up in different cultures, and culture means a lot. So the purpose of, and also that we should remind ourselves as scientists that the purpose of compulsory school is not, at least not only to recruit the future scientists. Many scientists have that as sort of back in their head, that in order to become a scientist you should learn that and that at an early stage, and that the curriculum should reflect that. But I think, I would argue, this is a completely wrong way of thinking about obligatory, compulsory schooling. And I also think that the we should have, when we are looking at, for instance, testing and results from rankings, we should keep in mind that a lifelong perspective is much more important than to have high scores at the age of 15, which is usual the testing age, for instance, for the Pisa project, and even before that on the TIMSS project. And that attitudes and values are important for several reasons. They are important as learning goals. In many countries, the attitudes and values are key cornerstones in the priorities in the national curriculum. And what is even more important, or equally important, that they are also the key determinants of future behavior, future choices. The values, attitudes, interests, motivation, and so on, in that sense, they are more important than actually knowing Ohm's law or whatever it might be, or solving equations. And of course, they are probably even more important for the great majority of kids who do not want to choose or do not or cannot choose science and technology, engineering, research, and so on for the future. That's only a minority, and we think we really have to think about the majority. And what we've seen from research is that when the science contents, and I would say also the mathematics contents, is forgotten, something remains. We could call it the body language of the subject. You could call it the ethos. You could call it the atmosphere. They do remember. So when you talk to people and say that you are a theoretical physicist, for instance, I'm sure you get some sort of reactions. And if you say I'm a mathematician, they've forgotten all the mathematics they had at school, but something remains. And it's not always a pleasure to hear what they have to say about how they think a mathematician or a physicist is like. And we have research to support that. And that remains for life. They have forgotten the little mathematics they learned, but they hate the subject the rest of their life, and they have a lot of preconceptions about what it is. Not preconceptions, but they have actually learned it in schools. So it's a concept that is learned at school. So, and I think a key concern for school science should be to promote lasting curiosity and interest and appreciation and respect for science and technology, understanding something of the nature of science and technology, the values, the limitations that come with it, and science and technology as part of culture and also as a cornerstone in democracy and sharing the values of a democracy. And moreover, we see from these tests that I'm coming back to, or shall start to come to, that if you look at results from different countries, you see in some countries they are on top of the score at the age of 15, but the same students actually hate the subject. So what's happening with these kids 15 years later? What will they choose, and how will they be? I have some data here. As scientists, we need data. This is how Pisa, I will later explain what Pisa is, but when I travel around, I find that most taxi drivers all over the world have heard about Pisa. And they only know one thing about it, and that is that their own school system is lousy. That's what I have learned from the press coverage of Pisa and the panic that comes with the politicians. Now, this is the score of Pisa when science was the main subject, the main subject. On top here, and you may have heard that, is our neighbor in the north, Finland. They had the highest score. I mean, this is a country as a whole. These are the 15-year-olds, and then this is the average score that we are giving here in one number. They are on top. And by the way, Brazil takes part, so that's a good reason to talk about it here. And as you can see, they are not at the top. But the important thing is that the same students have been asked several questions about, did you like the subject? Would you like to learn more? Could you think about a career in this? Do you want to study this? So it's a collection of questions about, and they make a composite score which is called a science interest score. And the same pupils have these results. And now you see immediately Finland at the absolute bottom of that. So at least people who believe so strongly in Pisa, maybe at least they should not look just at the ranking, but they should look at more data. You can tell different stories with the same numbers or with the same wealth of numbers, success stories and failures. But what gets attention is often just the ranking and not, say, this one, which is interest. And you see Brazil here. So actually people leave at 15, they leave school and they have some interest in science. Whether they get the possibility to study or take it further, that's another question. But the interest, at least, is there if we should believe in the PISA numbers. And sometimes I think we should believe in PISA numbers, not just the rankings. Now, international comparisons are important. I'm talking about education now, of course, mainly, but I think it's a wider implication. The positive with international comparisons that we get inspiration, we learn from others, we see that school is organized in a different way, subjects are different, and the contents of the subject, the teaching methods, everything can vary from country to country, and we can learn in the sense that we can get inspiration and get new ideas and take home from others. That's the positive side. Opening new perspectives and see alternative solutions. But, and this has become the dominant, and that has been the sort of focus of what we call comparative education. That is actually to learn from others and to map out the whole field and look at similarities and differences. But now we see that these large-scale studies, often we have trivializing of results and the stress on the rankings. And they are abused, misused, they are selectively used, just like I showed you. They concentrate on the ranking, on the score, and not on the interest, and a lot of other questions. Data are misinterpreted first by the press, and then by the press and the media, and then by politicians and policymakers. And it makes headlines and panic in the newspapers. And also that the priorities of each country, the national priorities of education, which are often negotiated in democratic, more or less democratic ways to become the education system as part of the culture, they are overruled or pushed aside by the strive to come higher up on the score on these international league tables. So they push aside the national priorities in education. And moreover, and I think this is equally damaging, there is a pressure to standardize and to a pressure towards a common, universal, and decontextualized curriculum. I'll come back to this issue of being decontextualized, that the context of education disappears in the strive to have universal indicators and testing by a universal test, which is the same across countries and countries. And it's creating political competition, panic and crisis, and the politicians or the party in power or the government feel that something needs to be done. But they have no clue about what. But they do something. And that varies in country to country, but some of these policies, and I may come back to that, are of the sort of standardization, more testing, commercialization, privatization, and competition. So neoliberal policies, to put it that way, new public management. Something needs to be done. And the reforms that are often introduced in different countries are unfounded. There is absolutely no evidence from these studies that this is a right policy. So whether a country is a success or a failure, it's up to the fantasy to sort of discuss why is it so, because it can say nothing about cause and effect by design of the study. I will probably come back to that, or we can take it in the discussion tomorrow if someone is interested. And winners often become models to be copied. Finland, for instance, I mean the good news for Finland is that they have got a new industry, and that is Pisa tourism. Experts come from all over the world to look what fantastic things they are doing in the classroom. Abu Dhabi want to buy Finland's education system. I think if they want to buy the education system in Finland, they have to buy the history, the language, and the culture and everything of Finland. And Abu Dhabi is indeed very, very different. They can't buy an education system. Now, there is a lot of, comparative education is a field on its own. And one of the basic textbooks on this is by Robin Alexander, and I have one statement of him here, or the basic tenet in the book and in comparative education is that life in schools and classroom is an aspect of the wider society, and the culture does not stop at the school gates. School, and we are talking now about primary or an obligatory school, is part of culture. Culture in comparative analysis and understanding, and certainly national education system, is all, says this key person in comparative education. And I think that's something we should keep in mind. Now, we have had international studies of education with us for a long time. They actually started some 50, 60 years ago. Which is also interesting, and I can come back to that because now we can follow some trends in what is happening. These are just some of the logos of studies. I don't know exactly which one that Brazil takes part in, but they certainly do take part in the most important, which I'll come to. And these studies, they come and go, or rather they don't go, they just come. And it's an abundance of them. Some of them get publicity, some don't get publicity. And when the OECD came in some 15 years ago with their Pisa project, gradually the others have lost or OECD has taken the scene. So now it is the Pisa project that really matters. Now, I guess everybody here would know some details about Pisa, but I will also give you, just to remind you, that it's driven by, the E in the OECD is, as you know, economy. And the basis of the OECD is to promote economical development in a free market economy. That's not an analysis of the OECD, that is the purpose, that is also OECD. What they are doing, so the E in the OECD is economy, it's not education. So when they enter education, it is because they think that this, or looking at the role in economic development. And that's probably why the panic also comes, because people think that they actually measure future progress and success in education, in the economy. But the testing is every third year. They are testing a representative sample of 15-year-olds, or rather 15-year-olds who are in school. So in some countries, not the whole population is in school, but so they are testing those 15-year-olds that are still in school. And the focus of the first testing was reading literacy. 3 years later, mathematics literacy. And then it was science literacy, and then it starts again with reading, mathematics, and the last one was in 2015 in science, and the results will come at December the 5th this year at 10 GMT. And there will be a press conference all over the world, and the results, and the winner is, and we will have the results, and the next day there will be tsunamis coming in all countries about this. Now there are 70 countries taking part. Now about 70 countries, and the testing time is 2 hours and half an hour of background questions. It's interesting to note that the OECD and this study is made for the rich countries in the OECD. These are the club of the Organization for Economic Cooperation and Development, OECD. As I mentioned, it is a rich man's club, not rich man's, but rich countries club, highly industrialized, It was established after the war, where the E was Europe at that time, and as part of the Marshall Plan to get the economy going after the war in Europe, and to protect Europe from communism, actually, to get the wheels going in a market-driven economy. That was the purpose of OECD, and OECD has changed, so now Japan is a member, and it's 35 of the 35 richest countries in the world. But 35 other countries also take part. They are not rich, but they want to be rich. And then they think that they should use the test which is designed for a country which is highly industrialized, and to use that as a measure also of their own education system, which is flawed by even in the beginning. And it's not the intention of the OECD originally. Now they test for 2 hours, and all these subjects are part of the testing each time. But one subject is, or rather one area, is in focus every time. And so the results that will come on December 5th will be science again as a main focus, and it will be, of course, interesting to note, to see results, but not only the rankings, but all the other things they get from the questionnaires. And the plans are there for a long time. Now, this is kind of, I mean, this is the economy or social science response to big global things like big science, techno-science, like we have in NASA and CERN, because there are tens of thousands of people involved. It costs large sums, at least for social science. Large sums involves thousands of people, and in addition, of course, schools and teachers, and it costs also a rather large sum of money. And it has become the key element in educational policy in nearly all participating countries. And this is not something that the critics say, this is something that the OECD is proud to announce, that they are influencing what is going on in schools. And I will come back with a quote on that. Some features of the Pisa test, this 2-hour test. I mean, no test is better than the items, than the questions asked. So you have to look at what are they testing and how are they testing it. And they say explicitly, we are not testing school knowledge. And the items in science, for instance, should not look like questions that you ask in science lessons in school. And they are explicitly not related to curricula in any countries. They test after a curriculum that is made up by OECD experts. I mean, these are good experts. The science and math people there are very good. But they produce a framework for testing which is unrelated to what's going on in schools. But they test what they think is worthwhile knowledge and skills. And of course, they are testing some aspects of only reading, science, and math. And for instance, for science, they are of course not testing anything like experimental skills, not field work, or all these things that should be part of good science teaching. In fact, the Pisa results correlate negatively with raising hypotheses and testing hypotheses, or doing experimental work, and using ICT. Pisa results correlate negatively with these things, and only that, I think, should make us think twice about putting too much weight on it. It's testing, it's a test that is a written test, pen and paper. And of course, we are talking about school. They are not testing social sciences, civics, history, geography, culture, ethics, foreign language, crafts, whatever. Everything else is neglected or not tested. And of course, they are not addressing, which is important in schools, values, solidarity, empathy, care, a lot of other sustainable development, and so on. So they are addressing just the minor or very little of what the school should be about. And also the fair testing, of course, the people working there are of course, they are top psychometricians, statisticians. They know psychological testing. And if the test is supposed to be fair, then they have field testing of items, and if it functions well in one country and not in another one, they can't use that item. So if there is, for instance, anything that relates to, say, my world, with ice and snow and polar conditions and oil drilling and fishing in the sea and so on, and the items, the issues that are on our public agenda, that has to be taken away because that's unfair to, say, Brazil or whatever country, or some other countries. So there is no national context, there is no context at all, because that is unfair to those who don't have that context. And good teaching, of course, and we are talking about primary, secondary school, good teaching at that level should always be based on things that are meaningful for the learner. And the learners are different in Brazil and in Norway, I can assure you. And still, in spite of all these things that I just mentioned briefly here, these rankings and scores are presented by the organizers and understood by the politicians and the media as a global and objective measure for the quality and efficiency of the entire school system, in spite of all these obvious problems that I just mentioned briefly here. And what they are claiming to measure, this was in 1999, the 1 year before the testing took place. They wrote, and it has been repeated since, this is what they test. How well are young adults prepared to meet the challenges of the future? They have a crystal ball. Are they able to analyze, reason, and communicate their ideas effectively? Very brave. Do they have the capacity to continue learning throughout life? And this is repeated in all later reports, also the last one. And this they managed to measure with a 2.5-hour paper and pencil test in solitude. And then they measure how well they can communicate ideas effectively, but they are not allowed to communicate with each other and not with the internet or anything. So, I mean, they are not exactly, I call this hybris. They are overselling what they are doing. That's how they are presenting it, and with items that are identical worldwide. So this, they said, a fantastic test. If there was a Nobel Prize for future research or psychology or sociology, this test would certainly have got many of those. And this is what they said in 1999, and it has been repeated ever since. So when I see that, I think this, yeah, they say they are testing real-life challenges. Real-life challenges for 15-year-olds, and they are supposed to be common all over the world. So a challenge for kids at that age, at 15 in Brazil, are supposed to be the same as in the US, in Mexico, and Ghana, and Norway. And real-life situation. Real-life situation here, the real-life situation is sitting at a desk and answering a questionnaire. And they say they are using authentic texts. It's based, and which is true in one way. This is something that has been on print in one of the 70 countries and is chosen by some mechanism to be part of the test after trials, and then it's translated to all the other languages and used. But then, of course, a text that was on a Norwegian newspaper at one time cannot be an authentic text when it travels the way to Brazil, of course. And the translation problem is also another issue. Yeah, so all current issues have to be removed because no country should be favored, and controversial and socio-scientific contents have to be removed because that can be controversial in some country, and they don't like controversies. For instance, in the other test, the TIMSS test, there is nothing about evolution, because that's controversial, not in most countries, but in, as you know, in the US and I think Libya. And very much it's also a test of loyalty and perseverance, whether you are willing as a 15-year-old to be presented this and to do your best, and it's anonymous, and it doesn't matter for the pupil, it has no consequence, they are never getting the chance to discuss the items, and even for the teacher and for the school it's anonymous, so there is no feedback to the school, they only use time to produce these data for this test. No feedback, no consequence. It's low-stake testing for the children, but of course for the government it's high-stakes testing because governments are compared. And you should really have a look at the few items and make your own judgment. Some of them, I mean, the test is of course secret because they have, in order to have timeline, they have to use at least most of the items as a bridge to the next testing round in order to say something about trend in time. So, but some items are released and it's very easy to find them. And if you like, I have also written some articles with a lot of references to critical research because now there is a lot of it. Yeah, Pisa testing in real-world challenges, authentic context. I see you did well in school, but what real-world skills do you have? Tests, I can take tests. I think at the very best, this is what they are testing. And there are some underlying assumptions here. And I dare to call it a neoliberal ideology, that competition in free market leads always to higher quality. So competition and free market is an assumption. And this competition between countries are compared between school districts, because now we have tests for that, between schools, between teachers, between pupils. That's considered to be good. Always good. And followed by publication of results, because it's called transparency, of course, accountability and transparency. These are very positive words, and you can't really be against it until you unpack and see really what it means. So these results from these tests are published, and we have got national testing where you can compare schools and school districts, and much of these reforms have followed after the Pisa testing. And competition and rankings, of course, require indicators, and at best universal indicators and reliable measurements. And these are details, but they are constructed. These indicators are constructed by the OECD, and it's called governance by numbers or governance by indicators. They don't have. The OECD has no formal right or power, but they rule by making indicators for schools, for the economy, and society in general. And now this has emerged as a universal indicator for school quality, and it's used in reports worldwide. And they give policy advice, which of course is unwarranted based on the format of the testing, cannot of course tell you what you should do. So now the tests, and the Pisa test is in particular in mind here. They have become a driving force for national reforms in most countries. And the underlying reason is, of course, that we are lagging behind in the global techno-scientific competition. And the OECD, since this is the club of the rich countries, advice from them or rankings from them is considered to be objective and neutral and scientific, so they get a lot of power because of this, and predicted for the competitive power of the nation. And this is the leader of the Pisa and related projects, Andreas Schleicher, in a TED talk. And the first words in his presentation here is that Pisa is really a story on how international comparisons have globalized the field of education that we usually treat as an affair of domestic policy. So they are proud to say that what used to be domestic policy for each country, now we have lifted it up to become a global concern with, of course, with standards set by the Pisa. And when they present the results, this is a map of countries taking part, or rather it's a map of the world with the countries represented here. And they present it as 80% of the world economy. I would say if education is for children, that's a very strange way of counting children. 80% of the world economy. And it has impact worldwide. This is, well, she's not Prime Minister any longer, Julia Gillard in Australia. By 2025, Australia should be top 5 in the world, and the government will use Pisa to track Australia's progress. So she's actually saying the same as you can find in most countries, many countries, is that the target of our education system, the measure of quality, will be the scores on this single test. And we will strive for that. So forget about our national curriculum, we have this as our target. And this is how it is presented in the US. This is again Andreas Schleicher. And you see the heading of the press conference, are American students unprepared for the global economy? That's what they claim to measure, how well we are prepared to compete. The lessons learned from Pisa and so on should inform US policy so that our students graduate ready to compete, thrive and lead in the global economy in the 21st century. So this is actually also how they themselves present results in the press conference, and hence, of course, the panic. And US government statement on Tims and Pearls, a number of nations are out-educating us, as if it was sort of a race or a Olympic game in the STEM disciplines, and if we don't turn around, they will soon be out competing us in a knowledge-based global economy. These are the words from the American US government, Arne Duncan, who was Minister of Education at that time. And Wall Street Journals on the front page, so you find it everywhere. Competitors still beat the US in math and science tests, and this is considered by the Wall Street Journal to be a tragedy for the nation. Now this tragedy has actually lasted for 40 years because the first signs of this failing of American schools is now 40 years old. And they are still falling, to put it that way. And this is Cameron in the UK. We are in the global, and this is about Pisa as well and testing. Sink or swim, do or decline. That's an order of march for the schools. And also Obama, race to the top, that's the system that Obama introduced in the US, will enable American students to outcompete any worker anywhere in the world. That's nearly a kind of declaration of economic war, at least, to outcompete anywhere in the world. And in my little country, when the results came, we thought we had a good school, but then came a new government, actually a right-wing government, and this minister, after having been in office for just 1 month, got the Pisa rankings on the table, and she really used that for all it's worth and not worth. Norway is a school loser. Now it's scientifically documented, and she said, this is disappointing, like coming home from the Winter Olympics without a single medal to Norway. And if you happen to know one thing about Norway, this would be a national disaster. We came home with 3 small medals from Rio, by the way, but that's the Summer Olympics and it doesn't count. And she added to this, and this time we cannot explain it by blaming the Finnish to be doped. And it is a history behind that, because Finnish skiers were caught in doping on a world championship which they arranged themselves, and it has been a tragedy, and people in the north do remember this. She said it on the press conference, and the Pisa was used to change Norwegian schools, introduce a new curriculum, and to introduce national testing, and the same was done in Sweden and Denmark, because we were also I mean, if Norway is not a winner, it's considered to be a loser. And of course, they can't all be on top. But it was used and abused, I would say, in all the Nordic countries to reform schools in a wrong direction. And you don't need to learn a lot of German in order to see the headlines here. Schule macht dumm, schools make you stupid. And that is also the Pisa being announced in Germany. The good news, obviously bad results are sometimes good news. So if you are working in science and math education, say in Germany, they got a fantastic funding for making new curricula and running in-service teaching training courses and so on. So they've done a lot of good things, but the argument was the Pisa test. It's a little like the US when they got the Sputnik shock, when Russians made the Sputnik. And that was the years that followed. A lot of very, I would say, progressive science teaching was produced in the US. But the money came after the shock. And then later on they got the Toyota shock, and now they got the Pisa shock. So 3 tsunamis they have had. But underlying this is, of course, what is taken for granted, and that is that this is really Pisa, and probably also the TIMSS, which is another of these large studies which have been around for a long time. I was, by the way, national research leader for Norway, taking part in the first TIMSS study in Norway. So I worked 3 years on the inside of these studies, and these 3 years became a kind of vaccination for me. At least I came out not being resistant, but rather with my immune defense somewhat stronger when I look at how these studies are used, because I know if you want to win, you can do a lot of things. If we want to beat Sweden, which is important in Norway, our neighbor, I'm half Swedish, by the way, so I win anyway. But if you want to do that, there are lots of small things you can choose when you translate items, when you reject some data and not some others. Lots of small and big decisions. So if you just want to climb a little, which is important here, you can make all these choices in one direction. There were some East Bloc countries taking part, and they deliberately, they said openly, and then they got the chance to travel to the West, go to conferences in Washington and in London, and they say, as long as we win, we will get this money and be able to travel. So we do the study accordingly. So of course they managed to be, Hungary was top, and now they are no longer on the top. But it looks very objective, but if you look at the details and how many decisions you have to take as a leader there, you can really try to get up and down with your results. But the taken for granted is that the score is the key to economical competitiveness. There was an article in New Scientist that put me on the lead here, and the main message there is that the common sense, it sounds natural that if you're young people at the age of 15 score high on science and math, that will be good for the future economy. It sounds it sounds sort of common sense. But this article says that it doesn't make, now we can actually calculate this, and we can look at these data in many ways. And the TIMSS items or the TIMSS studies have been with us for 50, 60 years. So what these authors have done, and now many others, now they can follow the winners and the losers if they are industrialized countries. I mean, they have to be comparable. And if you follow the cohorts, say 20, 30, 40 years after the bad results on these rankings, and they find there is absolutely no correlation at all between economical progress and a lot of indicators that are used for measuring that, number of patents and development of GDP per capita, equity, and other things. They don't correlate with measures of prosperity and future success, and the same now with the Pisa project, which has been with us now for 15, 16 years. So the panic, I mean, take Japan as an example. They have been on top of these rankings for 30 years, or nearly 40 years. And the US has been close to the bottom, actually, of the rich industrialized countries. So there is absolutely no, they become good test takers and bad risk takers is one of the things they argue from these. I have references in my some of my articles here. Now, and it's no surprise, I think, that Pisa has really become part of the global. I mean, they believe so much in privatization and standardization, and now they have become part of the economy themselves. They have a strong cooperation with Pearson. Anyone here who knows, I've heard the name Pearson? Yes, some? They are in Brazil as well, I found out. They have got an alliance. Pearson is the world's largest global actor on education. And this is from The Guardian. Should Pearson, a giant multinational, be influencing our education policy? That's in the UK. They are the world's largest. Some 80,000 people employed in 80 countries. And they are selling tests and textbooks and education systems. And now the new thing is that they are, and this is a joint press release from Pisa, OECD, and Pearson. Pearson is going to develop the frameworks, which is the curriculum for the next testing round. And this is actually a quote. Pearson, the world's leading learning company, today announces that it won a competitive tender by the OECD to develop the framework for Pisa 2018, the coming Pisa. And the framework will define what will be measured in Pisa 2018, now in the hands of Pearson. I mean, they are not doing it themselves. They are using experts, but they are behind this. And how this will be reported and which approach will be chosen for development tests and questionnaires. So now they won this bid. Of course, this is a strategic move from the world's largest contractor in education, because then they have all this. They have these contacts with top educators around the world, and of course that's a strategic investment for. It's, by the way, it's venture capital behind Pearson. So Pearson is commercial. It's venture capital, and they demand money from their investments. And they also produce what's called a learning curve. Pisa is every 3 years, but sort of in the middle between those, they need another shock. So they have created this, what I call the learning curve. And that's a cooperation also with the OECD. Ranking of countries. This is not published, this is not presented in international conferences in education. These are reports and are given to the governments and to the media. So it's not discussed in education conferences and possibly been torn apart by colleagues. It's presented in glossy, fine reports with lots of graphs, and it looks very convincing. So what they are doing, they sell you the test for the diagnosis of your sickness. They tell you you are sick, you need medicine. They create the medicine and the panic, and then they sell you the medicine, and they monitor how your progress is. So they have all the production line in this, and it's really, really big business. It's the fastest growing economic sector in the world. That's the education sector, where public money can find its way to private pockets. And this is widening, even widening, that Pisa is widening its scope, and in cooperation with Pearson and other providers of commercial interests, they have the Pisa based for schools, because now they have no power over the schools, because you can't really report to the schools. It's not by how the test is made, but they have made a special test that where the schools or the school district can compare themselves with, say, Shanghai, which is on top of the rankings. And of course, this is a commercial product that is sold, and the market is large. And they're also now producing Pisa for development, because for developing countries, they want to use this in cooperation with the World Bank also. And it's often used then as in order to get help for the education system in developing countries. They can use the Pisa test as a baseline to monitor progress on this, and also Pearson can sell them private schools and private tuition. So money floats back, money that we give in development aid from rich countries float back through these commercial companies. And also monitoring down to kindergarten and preschool. It's important to start early if you want to be effective producers in the market. Then you have to start at kindergarten. So they have also some projects related to that. And on top of this, the latest one is the Pisa for adults. OECD Skills Outlook. Pisa for adults. This is also huge, and it's run by the same group. Interviews with a sample of 5,000 or much more, door to door, face to face, and how they relate to literacy, numeracy, and problem solving in ICT-rich environment. Of course, I think there is a lot of very interesting information in that. But of course, that also creates the whole thing. They define what is important, and those who define the indicators also define the political agenda and create the panic and the needs in each country. And are we getting? Yes, we are getting close to. And Pearson buys Brazilian school chain. This I found some days ago. Currently receives more than 4/5 of the sales, aiming to increase its presence in emerging markets. And of course, Brazil is really one of those. But they don't seem to like the Latin America's biggest economy stalling, and intervention is center-left governments. Now you probably got rid of that in Brazil. I don't know, but we follow the news, but Pearson is there, and they have established lots and lots of private schools also. This is in the US. Are we prepared to hand over our children, our teachers, and our definitional knowledge to Pearson? So this is really a worldwide phenomenon to commercialize education. And the global education industry is really huge. If you look at the money, in each country, a large part of the national budget is of course large part is going to health, which is also more and more privatized, but a similar large sum is going to schools and education, and that is a market which is now emerging to be very interesting for commercial interest, and that demands standardization so they can use one size fits all across countries, and to develop systems for that, for sale. Now, when some critics say that Pisa has had a large impact on the policies, many politicians say, no, our policy is our own. You are wrong. It's not. They are not influencing our policy. So, but if we trust the OECD, and of course sometimes we have to trust the OECD, it's not a conspiracy at all. They give different advice. They have made a large report here where they are going carefully through what is happening in this case, the OECD countries, and Brazil is not one of those. So they are exploring the normative effects of the Pisa project, and they are proud to announce that this is the list, and they make a ranking of course, countries with high interest, with large influence. But the important thing is the first thing in the abstract. Pisa has been accepted as a reliable instrument for benchmarking student performance worldwide, and Pisa results have had an influence on policy reforms in the majority of participating countries and economies. That's their own, and originally developed as an instrument for the OECD countries. Pisa has been adopted as an almost global standard and is now used in 65 countries. And this is OECD's own conclusion on their review of educational policy worldwide. And yeah, well, these are Sweden, Denmark, Norway. It's not of interest for you so much. But there is now, what I'm saying here is, it's not very radical. If you look at professional journals in education, you see the critique coming. From many countries and from the best scholars in the education field. But they, of course, they write in their journals, academic journals, which are not read by politicians. And many of them refuse or do not take part in public debate, and they say if they do so, they will also not be friends with the government any longer, so the funding is a little in danger sometimes. And you see here, there were leading global school tests under attack. OECD accused of killing joy of learning, and this became this was an international action. And after a few days, there were scholars from 40 countries sort of subscribing to this document that was given to the OECD. Damaging education worldwide is the conclusion from these academics, and we still have the debate going on. Now I'm about to close, and so I'm coming back to my other hero, not Pablo Freire, because much of what I said here is influenced by ideals and values that I find in Pablo Freire's work. So I asked my other hero, Einstein, what he said about Pisa. Everything that can be counted doesn't count, and everything that counts cannot be counted, said Einstein, who was a physicist, philosopher, and artist. And if there are questions, comments, or protests, or whatever, there is a discussion session tomorrow, and I understand, is that the correct place? What we can learn and not learn from international studies, and that will give us a chance to explore in more detail if you're interested. Thank you very much. Thank you very much.
Thank you very much. Our time run out. I think that we should close. Maybe we have one or two quick questions.
Very interesting talk. After your talk, I became afraid of Pisa. But we live in a different world. Here, the politicians don't pay any attention to Pisa or to any other evaluation system. And the students they hate math and science. It's not an indication of the failure of our education. What's the alternative? What we can do?
I cannot answer that question, to be honest. I cannot. And education policy, I think basically education policy in each country has mainly to be negotiated by democratic means in that culture, in that society, which was also the quote I had. But we can certainly learn and get inspiration from others, and even from Pisa and TIMSS there are lots and lots to learn, but it has to be put in your own context. Traditions, culture.
Just this session tomorrow, there's not in the printed program, but is in the internet program, okay, that you can find that, but everybody welcome tomorrow. Cedro 1 at, 2 p.m. So, thank you very much.
Thank you.
Again, Sven, Professor Sven, thank you everybody.
That was a very interesting talk. Thank you. I followed your